Hello and welcome. In this video, we're going to be taking a look at another strategy of integration. Only this time, we're going to be really just focusing on integrals that are involving rational functions. Now, a rational function is where we have a polynomial in the numerator and a polynomial in the denominator. And sometimes we're lucky enough that we can just do a quick substitution, particularly if you just let u equal the denominator, that you might be able to complete that substitution method. But in many other circumstances, well, we have to take a look at that rational function and break it down into smaller components by using the method of decomposition into partial fractions. So let's see how that can play a role with various different integrals of rational functions. Well, let's start off with a couple basic cases and then see that we'll have to often use our method of partial fractions. We start off with a rational expression 2x over 3x squared plus 5. In this case, a substitution would be just sufficient. We would let u equal our denominator 3x squared plus 5. Now our du differential would be 6x dx. Now as long as our differential du appears in the numerator, apart from perhaps just a constant factor, then the substitution is going to work out well. Let's just maybe go for one more step. We'll replace the denominator with u, and dx will replace with du over 6x. So even though 2x and 6x are not the same, as long as they only differ by a factor that is simply a constant, then we can take this constant and move it out front of the integral, 2 over 6. Okay, well that is simply now just the antiderivative of 1 over u, and you can finish that question off. All right, let's take a look at another example where a simple substitution might work. In this example, I've got 2x plus 3 over x squared plus 9. Now, we'll try that substitution and see what happens. U equal to our denominator x squared plus 9. That means that du is equal to 2x dx. All right, I do have a 2x in the numerator, but 2x wouldn't be like a factor of the entire numerator since I have a second term there, plus 3, which is not divisible by 2x. Remember that we would need to have du to appear in the numerator, except for potentially a constant factor. But this isn't a constant factor, this plus 3 is an additional term, so that doesn't really work. But it's a quick fix just by splitting this into two separate fractions, 2x over x squared plus 9, and 3 over x squared plus 9 as well, and each of those could be integrated with a different strategy. The first integral can be using that same substitution where u equal x squared plus 9 and du equal 2x dx, and that will turn that integral simply into 1 over u du. But the second integral is a little bit more tricky. Let's try doing kind of an inverse substitution here. Let's actually let x equal 3 times a new variable. Maybe I shouldn't use u just so that I don't cause confusion. Why don't we let x equal 3t? All right, well, remember that we'll need the differential form. Dx will equal 3 dt. Now, how is that going to help us? Let's just take a look here. Replace the x with 3t. 3t squared is going to be 9t squared. Numerator 3, and dx is also 3, so that's multiplying 3 by 3 dt. Common factor of 9 in the denominator. 9 over 9 cancels, and this just becomes 1 over t squared plus 1 dt. Now, hopefully that will look a little bit familiar. That is actually just the derivative of arctangent of t. So the antiderivative of 1 over t squared plus 1 is arctangent of t. At this point in time, we'll just have to remember to plug in t is equal to x over 3. We kind of get this interesting result. We didn't necessarily see arctangents coming from this, but well, there we are. And it's also maybe just worth noting that if you have the natural logarithm of the absolute value of x squared plus 9, well, that's always going to be positive, which means that we can actually drop those absolute value signs and replace them with simply parentheses, since the absolute value of a positive number is itself. So be careful. We will end up occasionally with rational expressions like this ending up with arctangents in our answer. So it's good to just know a general formula for integration. In the case where we end up with the antiderivative of 1 over x squared plus a squared, that would be a perfect square there, that a is a constant, then rather than having to do that extra little substitution where we let x equal at, let's just turn this into a quick formula. this is equal to 1 over a times arctangent of x over a plus c. And that little formula there is going to become pretty vital if you happen to see that your denominator has something of the form x squared plus a squared. Not having a square root though. Oftentimes if we have the square root of x squared plus a squared, then we will have to make some kind of substitution. All right, now so far we haven't seen partial fractions at all. In these kind of cases, these are nice, simple, rational expressions that can be broken down into just quick substitutions. But let's take a look at the scenarios where suddenly partial fractions is really kind of a necessary strategy. Well, let's take a look at this example. We've got the indefinite integral of 3x minus 7 over x squared minus 2x minus 15. I could split this up into 3x over that denominator and minus 7 over that denominator. Unfortunately, the derivative of the denominator isn't going to exactly just be a factor of the numerator. So using that substitution method isn't going to work here. So we'll start to think about how we can break this down into easier rational expressions using the method of partial fractions. Now let's just review what steps we have to do with partial fractions. Remember that step 1 of decomposition into partial fractions is long division, and we only do that if the degree of the numerator is greater than or equal to the degree of the denominator. In this case, we don't have to do that since we have a linear numerator and a quadratic denominator. While skipping step 1, we're on to step 2 now, which is completely factoring the denominator and writing out into partial fraction forms for every one of those linear or quadratic factors. So let's come back to this integral in a moment and start off with step 2. Let's just take our rational expression, linear over quadratic, and see if we can factor that into two linear factors. If not, then we'll have to say that this is an irreducible quadratic. But we can factor this denominator. It can be factored into x plus 3 and x minus 5. Now that we've completely factored it down to irreducibles, in this case two linear factors that are non-repeated, then we'll use the partial fraction form for a linear non-repeated factor. For our first linear factor, x plus 3, the partial fraction form is a constant over x plus 3. And for our second linear factor, x minus 5, we'll have a different constant. We'll call it capital B over x minus 5. And we have no other factors left. Now, we're on to step 3, which is trying to figure out what these constants a and b must be. In order to solve for a and b, it's nice to multiply both sides of this equation by x plus 3 and x minus 5, which is our lowest common denominator. So multiplying both sides by x plus 3 and x minus 5 means that the left-hand side of the equation, we have both of those factors cancel out, and we're left with 3x minus 7. Multiplying the next term by x plus 3, that factor cancels out, and we have a times x minus 5. Multiplying b over x minus 5 by the factor x minus 5, well, that's going to cancel out, and we'll just have b times x plus 3. And there are a couple different strategies that you can use to solve for a and b. We can either equate coefficients of corresponding powers of x on left and right hand sides, or we can choose some convenient values of x, plug those in, and get a and b for a new value of x that we use each time. Now let's just say that we're going to make it easy when we have linear equations and choose to plug in convenient values of x. Let's say x is equal to 5. Well, then this equation becomes 3 times 5 minus 7 equals a times 5 minus 5, which is 0, plus b times 8. And right away, we can see that we must have to have b equal to 1. That one equation allows us to solve for one variable, but we need a second equation to solve for our second variable. To get the coefficient a, let's choose to have x equal negative 3. Plugging that into the left-hand side, 3 times negative 3 minus 7 is negative 16. And on the right-hand side, we'll have a times negative 3 minus 5, and that is negative 8a. That tells us a is equal to 2, because our term with b times x plus 3, well, that's going to become 0. So it's nice and easy to solve for a. Now that we've got a and b, we've really completed the method of partial fraction decomposition, but we haven't even started our integration yet. We have to come back to this original problem of the integral and split that up into partial fractions and integrate each of them individually. Our original integral now becomes an integral of a over x plus 3 and a second integral of 1 over x minus 5. Now, in the first integral, 2 is a constant and can be brought out front of the integral, and we have the integral of 1 over x plus 3 dx. And in our second integral, we don't have to worry about any constant multiples that we can bring out front. Each of these can be done with a substitution. In one case, we would have u equal to x plus 3, in which case du is equal to dx. And in the other circumstance, we will have to use v equal x minus 5, since I've already used u, and that means that dv is equal to dx. When you complete those substitutions and find the antiderivative, we'll end up with natural logarithms of absolute values of u and v, and we'll have to plug u and v back in. I'll skip a couple steps here and just say that in the end we end up with 2 times the natural logarithm of u, which is x plus 3, plus the natural logarithm of v, and that becomes x minus 5 when we plug that back in. And since this is an indefinite integral, we're not going to evaluate over an integral for x equal a and x equals b, but we're just going to have to remember to add that arbitrary constant plus c. Well, now that we've got the idea from this particular example, pretty much they're all going to look fairly similar. As long as we're very confident in our ability to be able to take a rational expression and decompose it into partial fractions, then we just end up with several integrals on their own. And, well, some of those are going to be u substitutions, and that may end up resulting in a natural logarithm in your answer. Some of them are u substitutions, especially if it's a repeated factor, where you're going to end up using the power rule. And also, sometimes we've seen that a rational expression will involve arctangent, where we have to use that nice little integration formula. So those are going to be kind of the solutions that you're going to expect for integrating rational expressions. Natural logarithms, powers, and arctangents. So let's try one more, and let's make sure that it's a little bit of a trickier one where we have to do a little bit more involved method of partial fractions. Okay, well, let's scale this up to this example where we have x to the 5 minus 4, all divided by x cubed plus 4x. Now, before we start jumping into trying to factor this, you'll notice that the degree of the numerator is larger than the degree of the denominator. So let's start off with doing some long division and try to break that up into a few easy terms to integrate, plus a remainder over x cubed plus 4x. Okay, well, we'll start by having our divisor x cubed plus 4x go into x to the 5 minus 4. However, it's really going to be useful if we leave ourselves lots of extra space here to write in all of the 0 terms. Now that we have all of those extra terms written out, it'll be easier to line things up. So we're going to be looking at the leading terms first and look at how many times we can add x cubed into x to the 5. X to the 5 divided by x cubed is x squared. So I'll put that here over the x squared column. And x squared times x cubed is x to the 5. And x squared times 4x is going to be 4x cubed. Now we're going to be subtracting that polynomial to see what the remainder is. And that remainder is simply going to be negative 4x cubed. And we can start bringing down some extra terms here to make our next process of division a little easier. Looking at the leading term of our remainder now, negative 4x cubed, well, we can still continue to do division since it has the same degree as our divisor. Negative 4x cubed divided by x cubed is just negative 4. So we'll multiply negative 4 by x cubed and negative 4 by 4x. And then we're going to subtract that polynomial, and we should get a remainder of 16x, and we'll bring down this minus 4. At this point in time, our remainder has a degree of 1, and we cannot do division anymore since our divisor has a degree of 3. This will allow us to change this integral into a few terms that are easier to integrate. When we do the division, we end up with the quotient x squared minus 4. Both of those terms are fairly easy to integrate on their own just by using power rules. The remainder, 16x minus 4, that gives us an easier rational expression to work with, 16x minus 4 over x cubed plus 4x. But we're still going to have to use the method of partial fractions on that additional term, since we can break that denominator up into a linear factor and a quadratic factor. So we'll come back to this integral here in a moment, and let's continue with partial fractions on 16x minus 4 over x cubed plus 4x. Now, we can certainly pull a common factor out of the numerator, but we're more interested in fact in the denominator with partial fractions. So I'm just going to keep that as 16x minus 4 for the time being. And then factor an x out of the denominator, and we end up with an irreducible quadratic, x squared plus 4. Okay, well that means that for our partial fraction forms, our linear factor x will have a partial fraction form of a over x, and our irreducible quadratic has a partial fraction form of a constant times x plus a constant. Since I've already used a, I'll use b and c. Okay, well, taking the equation here in parentheses, I'm just going to multiply left and right hand side of that equation by x times x squared plus 4. And that cancels out all of our denominators. Now in this case, since I have a quadratic factor, I'm going to use a method where I equate coefficients of corresponding powers of x on both sides of the equation. So I'll start off by writing out all of the coefficients for x squared in one color. On the left-hand side, I have 0 x squareds. On the left-hand side, I have 16 x's, and I have a constant of minus 4. On the right-hand side, after expanding, I'll have a times x squared, and I'll have bx times x. So combining those together, I have a plus b x squared. Distributing the x onto the c here will be the only term involving just x to the power 1. And the only way I'm going to get a constant on the right-hand side is when I distribute a onto that 4. Now, each of the corresponding coefficients on both sides of the equations must be equal to each other, since this equation must be true for any value of x. So 0 is going to equal a plus b, 16 is going to equal c, and negative 4 is going to equal 4a. Well, I know that c is equal to 16. This third equation allows me to see that a is equal to minus 1. And plugging that into my first equation, 0 equals negative 1 plus b means that b must equal 1. Now, I can take my a, b, and c, plug it back into my partial fraction forms, and rewrite 16x minus 4 over x cubed plus 4x. So, carrying on from where I left off in my integration problem, my initial integral turned into the integration of 3 separate terms, and that was done through division. And then, through more partial fractions, I've split up that final rational expression into 2 smaller ones. Now, going back to one of our first examples in this video, we saw this kind of scenario before, x plus 16 over x squared plus 4. It does make a lot of sense to actually even split that up into 2 separate fractions as well. Now, you can really see how this method of decomposition into partial fractions, whether it involves long division or not, is really just a technique for taking a very complicated rational expression and breaking it down into lots of easier integrals. I'll check these ones off one at a time. X squared, we can do that because that's a power rule. Minus 4, we can integrate that. That's just another constant function rule. And then our 1 over x, that's going to be a natural logarithm. For this first, a little more complicated looking rational expression, I can do a substitution. And this last one here, I can use that arctangent integration formula. So all 5 of those can now be integrated, and we can apply a different strategy on different terms. Looking at each of these as a separate integration problem, I'll use my power rule, my constant function rule, my 1 over x rule, a substitution where u equal x squared plus 4. Now that does mean that my du is going to be 2x, and that isn't quite exactly what I have in the numerator here. It's just off by a factor of a half. So after doing that substitution, I end up with 1/2 times the natural logarithm of x squared plus 4. And then last but not least, the 16 here is a common multiple. I can pull that out in front, and I have x squared plus a squared, where a is equal to 2. So using the integration formula, that would be 1/2 times arctangent of x over 2. Let's not forget that, plus c. And 16 times a half can be rewritten as 8. And x squared plus 4 is always positive, so I can drop those absolute value signs and turn them into parentheses. Now, if you feel like being a little cheeky, that 1/2 can even move up here and become a power by one of the properties of logarithms. We could even rewrite that as now a square root of x squared plus 4. I wouldn't say that's any easier to look at, but it's just something that you can do. And there we go. That's a little bit more of a complicated example of where we're going to use partial fractions to solve or evaluate an integral of a rational expression. Keep in mind that none of these examples used any kind of linear or quadratic factor that was repeated. So that can definitely happen, in which case then a repeated factor will have to have multiple partial fraction forms. But once you get the general idea, and you know that the result are probably going to involve logarithmic functions, power rules, and this arctangent trig formula, then you're going to be on the right path. So try lots of examples. This is definitely one of the more involved strategies. Maybe you like it better if you're more of an algebra fan versus a trigonometric kind of fan, but it definitely can be a long process. You do all this algebra off to the side, and then you eventually come back and you finally get to the integral again. So we'll look at other strategies for other challenging integration in the future, but that's it for now. Thanks for watching, and I'll see you in the next video.